Thank you, Professor Yuan, for the wonderful lecture on nanostructured polyionic liquids for energy and environmental applications. I see we have several questions coming in from the audience. We have collated some of them. So the first question is from a participant who is interested in knowing the kind of polymerization. So whether it's anionic, cationic, or radical. And just to follow up to that question, is catalyst needed for the polymerization?
Oh, that's just a very nice question. It's as I mentioned in the end, nanostructured polyionic liquids. It's a very nice topic to handle because the synthesis is extremely simple. You need no catalyst. You only need water and a thermal initiator. Here we use VA86. You can also use the other water-soluble initiator. You do not even need a stabilizer. That's monomer, water, initiator, and oil bus. So synthesis is extremely simple.
Okay. Thank you for providing insight into it. Moving on to the next question. Another participant wants to know if we can use these polyionic liquids, nanostructured polyionic liquids as electrolytes in high temperature water electrolysis for hydrogen production.
These polyionic liquids in a bulk state, they are not ion conductive, but they're used in electrochemical devices, for example, for the electrification of water by coating the electrode surface. And this coating make the ion transfer and electron transfer extremely efficient. So yes, they are indeed used in those applications, usually as a surface modifier to improve the efficiency.
Thank you, Professor Yuan, for answering the question. So moving on to the next question. Is it possible that polyionic liquids can recover selective metals from mixed metal solution? For example, more than 6 to 7 metals which have monovalent or divalent ions?
The question is yes. So we tested that already, that when you mix zinc and nickel with and also sodium, potassium, these are not at all absorbed by the porous membrane. If you consider gold and platinum as the target of recovery, the only interfering metal we saw is actually the iron that can slightly interfere. But not, even in the case of iron, the selectivity is sufficiently high. So the number you see in my talk, that you see some iron is recovered as well, simply because the concentration of iron is very high. In the real samples, usually the gold and the platinum in the electronic devices, the concentration is very low. Even at these low concentrations, you can absorb a lot of gold and the platinum over iron. So the selectivity is very high. Yes, I think my answer to your question, yes, you can selectively absorb the noble metals of our interest.
Okay, thank you. Thank you for giving that insight. Our next question from our participant is, what are the possible intermolecular interactions between ionic liquid and monomer? And what is the possible mechanism in changing the morphology from spherical, vesicle, and elliptical? Any insight into it?
That's a very nice question. Yes, we have been working on that for quite a long time. You are right. The intermolecular interaction here is quite complex. And classically, you would say you have the van der Waals interaction in between. This is true almost for all soft matters. What is here very special in the pure polymer is the hydrogen bonding. And the imidazolium has called let's say C2 protons. That is a proton, or that is hydrogen relatively active. If you come to the triazolium, you have actually two active hydrogen atoms. Both are active. So both can build up hydrogen bonds. And I have not shown here of another recent work. We use only pure PRL without polyacrylic acid. By using the hydrogen bonding, you can produce the nanoporous, well, not nanoporous, the porous PRL membrane purely by hydrogen bonding. Right? So here, the interaction mostly are the hydrogen bonds plus valent van der Waals interaction Of course, you have the charges. You know the charges give you the electrostatic interaction as well.
Okay, thank you. The next question refers to the battery application that you have shown. So in the graph of specific capacity versus cycle number, in one plot on the right, there is a sudden jump in the capacity towards the end of the cycle. Any insight why do we see this interesting feature?
Well, that is actually you tested the battery at different current densities, and you can see that at different densities, this can have a very, let's say, high, very good response can follow the current densities. It can recover stepwise from high to low, and it can recover back, right? Of course, batteries you want them to let's say fast charging and fast recharging, and some of you do not need fast charging, and these batteries can satisfy different needs in that purpose. And I forgot also in the previous question, someone was asking the transition from the spherical nanoparticles to the other
Mhm.
morphology. I think I skipped that question. Sorry for that. I just realized I did not answer that question. And if I go back to that question, when you have the spherical structure, in aqueous solution, the outer layer of the nanoparticles are actually the imidazolium bromide backbone because this is the hydrophilic fraction of the polymer. So they are located outside to stabilize the pure nanoparticles by electrostatic repulsion. And the surface, since the surface is in direct contact with water, so the hydrophobic aqueous chain, they try to avoid their contact with water. And in the case of the triazolium, so the triazole has much high, I would say, hydrophilic effect here. So the interaction between water and the triazine is much stronger than the interaction of imidazolium and water molecules. And this high interaction with water liberates some rooms for the aqueous chains. So the aqueous chains now they interact with water, which is unfavored somewhat dynamically, but this is now compensated by the strong interaction of the triazolium units, right? So in general, the surface energy is balanced. Um, so this gives you the relaxation of the centric laminar structure now to relax into parallel one. So the bending energy there is also very high. So it's a balance of the surface energy and the bending energy, right? These are interlocked by the microphase separation. So it depends on the thermodynamically which energy is favored by the interaction with water molecules.
Okay, thank you for explaining those things to the audience. The one of our participant is wants to know if there are any simpler polymerization initiated substitutes in forming polyionic liquids.
Most of the polymerization we carried out in water. The reason for that is very clear that water is green and the industry likes water very much, right? It has a minimum toxicity. And based on the solvent, we choose VA86 because it's water soluble. Of course, there are also different water soluble initiators and that you can choose as well. Just one point here is it's better to choose water soluble initiators with less ionic nature because if you choose ionic water soluble initiator, the ionic strength will impact the stability of the pure nanoparticles because the pure nanoparticles stabilized by electrostatic interaction here, right? So if you have ionic initiator that can influence their stability when you produce them in water.
So another question is on the mechanical stability of PIL film. So would you like to comment on the mechanical stability of PIL films for energy applications?
If the question is related to the polymeric film, the polymeric membrane is stable. When it is under mechanical stress, the dry film can be brittle. The film in a wet state is stable. And there is a recent, let's say, work that we have done to improve the mechanical stability by incorporating fibers. It can be either carbon nanotubes or use cellulose nanofibers. These are the fibrous structure you could introduce into the membrane fabrication process, so they can enhance the mechanical properties of the porous polymer membrane in required let's say devices. If the questions is related to the carbon membrane, yes, you are right. So if the carbon membrane you produce is not flat enough, you have bending on the surface. This make them brittle. So if you press them mechanically, and if the membrane is not flat, they do collapse along the along the assembly into the devices.
Okay, thank you. So this takes us to the last question of this talk, which is on, I think this you have already said during the talk. This is regarding gold recovery from e-waste. A participant wants to know, how do you separate the metals?
Well, the gold metal and the platinum is not easy to dissolve. Gold, you could really, let's say, dissolve them. This is the mining industry. This is how you produce gold from the minerals, right? It's by oxidative dissolution of gold, and then after that, you can reprecipitate it out. When you dissolve the gold, the left on the membrane is the platinum, and then you separate both. So the next step is to regenerate the gold metal by precipitation.
Okay. Just one last question. I think one participant is really eager to know, the adsorption capacity of the membrane. So he's interested in the units of the adsorption capacity of the membrane, whether it's gram per gram or milligram per gram. Again, on the gold recovery work, I
gram
think.
per gram is gram per 1 gram of membrane can take 2 times of its weight of metals.
Okay. Okay. I think that's it. Well, it seems that we have covered most of the questions that we received from the audience. And thank you, Professor Yuan, for responding to the queries from the audience. And
Thank
I'm
you
sure,
very much for the questions. And also this, I would say this is a very nice discussion in the end. Thank you so much.
and I'm sure that audience has immensely benefited from this engaging session. This is all from Q&A. Over to you, Neha, for any concluding remarks.
Thank you. Thank you so much for this interactive question and answer session.